So today we're going to find the mass of the solid bounded by the surfaces x is equal to the square root of y squared plus z squared and x is equal to 2 with a density function delta in respects to x, y, z is equal to 3x. So right here I already drawn out my region, this cone-like shape from 0 to the x equals 2 plane. And so what we're going to do is we're going to talk about the boundaries. So I'm going to set this in terms of E is going to be x, y, z. And we're going to talk about x. X is going from 0 to this function. Or excuse me, the x is going from this function to 2. So it's going to be the y squared plus z squared less than x to 2. And then now we're going to talk about y. But y is just going to be square root plus z squared. And since it's going to be to 2, we're going to set it equal to 2. I'm going to try to isolate y. So I'm going to take the square root of both sides. This becomes 4. This becomes y squared plus z squared. And so if I subtract it, and I took the square root, it's going to be plus and minus. So y is going to be bounded from negative square root of 4 minus z squared to positive 4 minus z squared. And then z is just going to be from negative 2 to 2. The reason why z is going to be from negative 2 to 2 is because if I were to look in perspective of the x is equal to 2, x is equal to 2 plane, right? I would set it up like, I would look at it in terms of the z and y plane. So y and then z. Right? And it would look somewhat like a circle. Recall that y squared plus z squared, it looks is the equation of a circle, is equal to 4. So, or we can look at it in terms of 2 squared, like we did earlier. Okay, so now that we got our boundaries, we're gonna try to find the mass. Recall that the equation of the mass is equal to the integral of the density function within this region. So what we're going to do is that we're going to set it up from negative 2 to 2. Oh, I'm going to write it like this. E of 3x dv. Okay? And if we were to write out the whole integral, be from negative 2 to 2, from negative square root of 4 minus z squared, 4 minus z squared, and then from the square root of y squared plus z squared of 2 to 2 of 3x, and then it's going to be from dx, dy, and dz. Looking at this, it seems pretty painful to take the integral of this because of the fact that there's so many square roots. So we're going to try a different method instead. How we're going to do this is that we're going to convert x, y, and z in terms of cylindrical coordinates. Recall that cylindrical coordinates is where I keep one variable the same and the rest I turn in terms of r and theta. So if I were to go to the cylindrical, in this case, since we're taking the density function in respect to x, I'm going to let x be kept the same. All right, and then now I want to change y and z in terms of r and theta. Looking at our circle, we can say that y is going to be something in terms of cosine. So we're going to say y is going to be equal to r cosine of theta, and z is going to be equal to r sine of theta. So now, what we can do is that we can change our limits. We can change our limits of integration as well as changing this integral entirely. So how this is going to look is that look at this. R is going to be we're going to be reaching from 0 to 2, and then theta is just going to be from 0 to 2 pi. So if I were to change our limits, I'm going to do 3x r dr, dx dr d theta, and then the square root of y squared plus z squared is just the square root of r cosine of theta squared plus r sine of theta squared, and we all know this is just going to be r. So in this case, it's going to be from r to 2, and then our r is going to be from 0 to 2, and our theta is going to be from 0 to 2 pi. So what we're going to have to do is we're going to have to integrate this in respects to x first, then dr, and then d theta. So because of lack of space, I'm going to just write it out right here, and I'll use a different pen. So the integral r2 of 3x r dx first with respect to that is going to be, so if we integrate this, it's going to be 3 over 2 x squared r, because we're keeping r as a constant, from 2 to r. So what this is going to turn out to be is going to be 3 over 2 squared r minus 3 over 2 r squared r, which is just going to be 2 squared is just 4 divided by 2, which is 2 times 3, 6r minus 3 over 2r to the third, right? So now what we're going to do is we're going to take this and we're going to integrate it with respect to r now from 0 to 2. So it's going to be from 0 to 2 of 6r minus 3 over 2 r cubed dr, right? Now this is going to be 3r squared minus, if this becomes 4, so this would be 8, minus 3 over 8 r to the fourth from 0 to 2, which is just going to be equal to the squared minus 3 over 8 2 to the fourth. I don't need to write 0 because the fact is they all become 0, so I'll write it from right here. So 3 times 2 squared is 4, so it's going to be 12. 2 to the fourth is going to be 16, divided by 8, which is 2, times 3, minus 6, so we have 6. Now, I'm going to integrate this in respects to theta. So, it's going to be the integral from 0 to 2 pi of 6 d theta, right? So this is going to turn into 6 theta from the limits to 0 to 2 pi. And recall that I don't need to subtract 0 considering the fact that 6 times 0 is 0. So it's just going to be 6 times 2 pi, which is just the equivalent of 2 pi. And so our mass is going to be equal to 12 pi. And that's our answer.